Dear viewers, welcome back to the TCE Made Easy series of civil engineering concepts. In this example, we will see the step-by-step procedure of analyzing a portal frame using moment distribution method. So this is the portal frame which is to be analyzed. So this height of column is 3 meters, span of the beam is 6 meters, and height of this column is 3 meters. Moment of inertia of columns I, moment of inertia of beam 2I, subjected to UDL of 12 kilonewton per meter. First step will be stiffness and relative stiffness. So write the span. We have span AB, BC and CD. So AB, BC and CD. Length of AB is 3 meters, BC is 6 meters and CD is 3 meters. Right, moment of inertia. Moment of inertia of this AB is I, BC is 2I and CD is I. Stiffness. If I consider support A, it is fixed and B is continuous, C is continuous and D is fixed. Here no support is freely supported or hinged. So 3 by 4 I by L will not arise here. So everything will be I by L. So here I divided by 3, here 2I divided by 6 and here I divided by 3. If we simplify, this is I by 3 and this will also be I by 3 because 2 and 6 will get cancelled, we will get I by 3. This is I by 3. Therefore, the common multiplier would be, if we multiply by 3 by I, we will be getting the relative stiffness. So multiply by 3 and divide by I. So 1, 1, 1 will be the relative stiffness. Then step 2, distribution factors. So distribution factor for AB, df AB equal to 0 since A is fixed. Then df distribution factor for BA will be equal to stiffness of this member by sum of stiffness of members meeting at the joint B. So KBA divided by KBA plus KBC will be the distribution factor for BA. Then distribution factor for BC will be KBC divided by KBA plus KBC. The similar way, distribution factor for CB will be KCB by KCB plus KCD. And distribution factor for CD will be KCD divided by KCB plus KCD. Then distribution factor for DC will be 0 since D is fixed. So using that, the K values which we have here as the relative stiffness, substituting, will be getting the distribution factors at for every member. Then we need to find the fixer end moments. So in this portal frame, there is a beam subjected to UDL. Therefore, if we treat it as a fixed beam, then fixed end moment will be minus WL squared by 12 and plus WL squared by 12. Therefore, that will be the fixed end moment. So minus 36 kilonewton meter and plus 36 kilonewton meter. Now the step 4, that is moment distribution. So first write the joint. We have joint A, joint B, joint C and joint D. Write the members. At A we have only one member AB. At B we have two members BA and BC. At C also we have two members CB and CD. At D we have DC. So write the member. Then write the relative stiffness. Everything is 1 in this case. Then distribution factor for A is 0 since A is fixed. And DFBA we have found as 0.5, DFBC we have found as 0.5, DFCB we have found as 0.5 and DFCD 0.5 and DFDC will be 0 since D is fixed. First write the fixer end moment. So fixer end moment will be for AB and BA 0. For BC and CB we have minus 36 and plus 36 applying the previous step. Then DFCD fixer end moment at CD and DC will be 0. Now straight away we can start the distributed end moment because we don't have any freely supported end. If you have any freely supported end, then the moment at that end need to be balanced and of the moment need to be carried over to the far end. And then finalize with the finalized fixed end moment only we should do the process of DEM, COM, etc. So here we can straight away start the distributed end moment DEM. So for distributed end moment, consider every joint. So if you consider joint A, the moment is 0, so the distribution factor is also 0, therefore moment to be distributed in moment is 0. When you come to joint B, we have 0 minus 36. So the unbalanced moment is 36. Okay. So 0 minus 36. So 30, if you apply plus 36, then it will become 0. Therefore 36 is the balancing moment. So 36 multiplied with this distribution factor will give you this moment, and 36 multiplied with this factor will give you this moment. Similarly, here 36 and 0 are there. Therefore, unbalanced moment is 36. So we need to balance by applying minus 36. So this minus 36 multiplied by corresponding distribution factor will be minus 18, minus 18. So this completes first cycle. In the second cycle, we should start with carryover moment, COM. So COM, carryover moment, should be done within the members. That is from AB to BA, BA to AB, BC to CB, CB to BC, and CD to DC, and DC to CD. Likewise, you should do the carryover moment. So here AB is here, half the moment will be carried over to BA, so 0, 0. Here 18 is here, so half the moment 9 will be carried over here. When you come here, 18, BC, we have 18, half moment will be 9. And at CB, we have minus 18, so half the moment will be minus 9. And here minus 18 for minus 9 and 0 here. Now distribute in a moment. So consider joint A, we have 9. So minus 9 need to be applied. That minus 9 multiplied by corresponding distribution factor will be 0. Then 0 and minus 9 is here. So balancing will be plus 9. This plus 9 multiplied by 0.5 will be 4.5 here. Plus 9 multiplied by this 0.5 will be 4.5 here. Then coming to joint C, we have 9, 0. Therefore, minus 9 is the balancing moment. Minus 9 multiplied by 0.5 will be minus 4.5. Minus 9 multiplied by 0.5 will be minus 4.5. Here, minus 9 is there. Therefore, balancing moment is plus 9 multiplied by the corresponding distribution factor 0 will give you 0. This completes the second cycle. Then third cycle, carryover moment. Half the moment need to be carried over. So, you draw the arrow here for one iteration. The same arrow can be followed for all the iterations. So AB to BA, BA to AB, BC to CB, CB to BC, and CD to DC, DC to CD. So likewise, you need to carry over. So 4.5 half will be 2.25, here 0, here minus 2.25, plus 2.25, 0 and minus 2.25. Again, distributed moment. Here we have 2.25, so balancing moment will be minus 2.25 multiplied by the corresponding distribution factor will be 0, therefore 0. Then coming here, 0 minus 2.25 is here. So to balance, we need to apply plus 2.25. This plus 2.25 multiplied by corresponding distribution factor will be 1.125 and 1.125. Here we have minus 2.25. So 2.25 plus 0, therefore balance mode will be minus 2.25. Minus 2.25 multiplied by this 0.5 will be this and this. Next, the fourth iteration, carryover moment. Half moment will be carried over here, half will be carried over here, half moment will be carried over here, half will be carried over here and here. Then with this, we need to do the distributed moment as we did before. So this, we have 4 cycles or 4 iterations. We need to add from this fixed moment to get the final moments. So if I add from here 0, 0, 9, 0, 2.250 and 0.5630, you will be getting 11.813. That is the end moment at AB. MAB is this moment. Then here, if you start from here, you can add. You should not add the values which are written within the bracket. Say they are nothing but the balancing moments marked. So preferably to do this with pencil so that we will not get confused with these values. So here I get we get 23.91 and here we get minus 23.91. If we add from here, we'll be getting this value 23.91, here minus 23.91, minus 11.813. So these are the final moments. Then we very well know that at any joint or support other than the fixed support, there should be balance of moments. So 23.91 minus 23.91. This 23.91 minus 23.91. Therefore, balance of moment has taken place. Then at fixed end moment, fixed end will be having some value, fixed moment. So these values. So with these values, we can start drawing the bending moment diagram. So how to draw the bending moment diagram? Let us see. Say the moment at MAB is 11.13. So plus 11.13 means clockwise. So stand here, apply a clockwise moment. Stand here, apply a clockwise moment and see where this column will be moved. Say whether it will move inside or outside. So if I apply a clockwise moment, this moment will push the member inside. Therefore, I have marked 11.83 here inside. Then coming to this point, we have 23.91 plus. So we need to apply a clockwise moment standing here. So apply a clockwise moment to this member AB. So this column will move out. So mark this 23.91 outside. Connect these two. So this completes the bending moment diagram for the column. Coming to the beam, here we have minus 23.91. So stand here, apply an anti-clockwise moment and see whether the beam, this beam will be pushed up or down. So if I stand here and apply an anti-clockwise moment, naturally this beam will be pushed up. So mark this value of 23.91 above here, above this point. Similarly, coming here, you'll be having plus 23.91. So apply a clockwise moment here, it will push the beam up. Therefore, 23.91 mark here, connect these two, connect these two. Then coming to this column, we have minus 23.91 here, So apply an anti-clockwise movement to this column. Apply an anti-clockwise movement to this column. The column will be pushed out. Similarly, here we have minus 11.83, my 813. So apply an anti-clockwise movement here. So this will go and push the column inside. Okay, just see here, stand here, apply an anti-clockwise movement and see where the number will be pushed. So this is how we should draw the bending moment diagram. And here for columns we don't have any external loads, whereas for beam we have external loads. Therefore there will be free bending moment diagram. So here in this problem we have UDL. So UDL will make the free BMD will be WL squared by 8. So mark this free BMD. So this total ordinate will be WL squared by 8. If we deduct this value, we will be getting the positive bending moment here. So this is how we should complete the bending moment diagram. Thank you all for watching. Please subscribe our channel and make it reach many so that the concepts could be understood in a step-by-step procedure. Thank you.